Hello and welcome to video 5 for the solutions unit. This video covers colloids, suspensions, and then colligative properties of solutions. First of all, make sure you're taking some good notes with this. We have a lot of just concept-heavy details in this video, so prepare to take some notes, maybe pause as we go through and write a few things down. Particularly for discussion points, there's a full page of work in the practice packet pursuant to this stuff. First, we already know about true solutions. We use the word true because when we say solutions, we mean lots of things. So a true solution is a homogeneous mixture in which the particle sizes can't be separated by filtration. They're transparent. The solution is transparent, completely stable. Nothing settles out. Okay, when you make your ideal Kool-Aid, the red doesn't fall out of the solution. So we have a homogeneous mixture. And for definition purposes, particle size is less than 1 nanometer in diameter. This is just to give us a firm line of where we can say, oh, we have a solution or we have a colloid, which is our next topic. An example of a true solution is sugar water, but there are dozens. When you buy Gatorade, true solution. Okay, so let's move forward. The next type of solution is a colloid. A colloidal solution is a heterogeneous mixture containing particles that are intermediate in size between that of a true solution and a suspension. Okay, the suspension we'll talk about next. A colloidal solution can be solid, liquid, or gas mixed with any other phase. So you can have a gas colloid, technically. The reality is that's not common, but it can happen. The particles stay suspended, in other words, don't settle out because they have layers of charges that repel each other. Okay? The particles only settle out if something neutralizes those charges, and the particles are then attracted or repelling one another, and their density takes over and they settle out of the solution. A colloidal solution will exhibit the Tyndall effect. A Tyndall effect is a scattering of light when you shine light through the colloidal solution. Fog is a good example. When you drive through fog, your headlamps will light up all the fog and you can't see because you're white out. But if you take something more simple, like a glass of milk, you darken the room, put a flashlight up to it, you'll note the whole thing lights up. Similarly, Jello will do the same thing. Colloids move about erratically when you view them under a microscope, and the best example here is blood. When you look at a peripheral blood smear under a microscope, you'll notice that red blood cells and other particles in the blood will appear to be moving around chaotically. We call that Brownian motion. It has nothing to do with the fact that the charges that are interacting among the particles are allowing them to move around, be attracted and repelled constantly by the things around them. Examples of colloids include fog, milk, glue, blood, paint, smoke, foam, emulsion, gelatin, pumice rock, many other things. I don't need you to memorize the laundry list. I need you to understand what it constitutes and the particle sizes therein. The next type of solution is a suspension. A suspension contains particles larger than those in a solution that aren't colloidal, or they don't stay dissolved. They settle out over time. Generally, they're greater than 100 nanometers in diameter, certainly heterogeneous with discernible phases easily. When particles of suspension are in the suspension, in other words, say you agitated a suspension, the particles do reflect light and exhibit the Tyndall effect. And it's very easy to separate the particles of a suspension by filtration. The next key idea are the colligative properties of matter. This has to do with solutions because it's directly impacted by what we presently understand in solutions. So a colligative property of a solution depends only on the number of particles dissolved and nothing to do with the nature of the solute. Okay? Colligative properties change in response to you adding solute to the system. The amount of change in that colligative property is proportional to the number of particles you add to the solution. Okay? If you add a covalent compound to a solution, if you add equivalent values like 1 sucrose molecule, 1 formula unit sodium chloride, 1 formula unit calcium bromide, we're looking at equivalences here. So 1 sucrose molecule will yield 1 particle because that sucrose won't further break apart. Whereas sodium chloride, when you place it into water, will not only dissolve into sodium chloride, it will ionize and form sodium and chloride ions. So per formula unit, you'll get 2 particles. sodium ions, chloride ions, or sodium ion, Na plus, and chloride ion, Cl minus. Calcium bromides, much like sodium chloride, ionizes in water, and in doing so, you're going to receive 3 particles. That's because you have, for every calcium ion, you will have 2 bromides of 3 particles per formula unit. Therefore, all things being equal, calcium bromide would have the greatest impact on the colligative properties of a solution. The first property we need to understand, there's several colligative properties. We're only going to worry about 3. The first we're going to learn about is the decrease in vapor pressure. Solvents evaporate most easily when they are pure. So if a solute is added, less of the solvent is able to vaporize. And this is a very simplistic explanation, but it's adequate. There are fewer molecules at the surface of the solvent available to vaporize, and that's because they're occupied or attracted to this non-volatile solute. Non-volatile means it won't form a gas. Sodium chloride is an ionic compound. It's not going to form a gas in solution. So the attraction for these water molecules in the sodium and chloride ions is sufficient to limit the number of water molecules that escape the solution at a given temperature. Therefore, a decrease in vapor pressure. The second colligative property to discuss is the boiling point increase. Boiling point is equal to the temperature at which the vapor pressure of a solution is equal to the external pressure around the solution. And the logic here is that fewer molecules of the solvent are at the surface of a sample and available to vaporize at a given temperature. But the same thing is true. We have the solute particles attracted to the solvent and therefore limiting their ability to escape the solution given a particular energy. Applications of this particular colligative property include the use of antifreeze in engines and moving parts that increase in temperature, and then making spaghetti. Okay, making spaghetti, we add salt, not just add flavor, but to increase boiling point so we can get the nice al dente pasta. Ask in Italian. Anyway, so this principle is not lost on our things we currently understand. A good analogy, and I don't usually do these, but this is a good one, is that friends keep you cool. Okay, well, all right. These particles with their eyes eyelashedly shut are the solute particles surrounding a piece of solvent. And that solvent is inclined to reach its boiling point because it's surrounded by these solute particles. Again, the solute particles non-volatile, they can't escape the solution. And so they're attracted to this particle that can also have less of a probability of escaping because these particles are there. And the third colligative property, and the last we need to know, is the freezing point will decrease. If we add a solute to a solution, the freezing point of that solution then drops. And the reason being, the solute, for the same reason, physically obstructs that solvent from forming crystals. The crystalline structure of the substance is less likely to form when you have this solute in the way, attracting to the particles of the solvent. And that pushes freezing point lower. We typically expect water to freeze at about 32 Fahrenheit. Arctic waters freeze much lower than that, A, because they're salt water, B, because they're moving. But the added salt definitely contributes greatly to the fact that Arctic waters freeze below freezing temperature for water. And the other example is, and most importantly to us, is we use rock salt to melt ice. Not just to clear the pavement of ice, but also to make ice cream. Where would we be without ice cream? Well, probably thinner, but that's it. But friends keep you from freezing. Same thing, similar principle. When water particles are surrounded by these solute particles that are attracted to the water, they limit water's ability to freeze, just like they limit water's ability to boil. So you can imagine that adding a solute increases the breadth of the liquid phase of water. Okay, it's harder to boil, it's harder to freeze. Okay, so it sort of fattens that middle part of a phase change curve for water. Again, the non-volatile solute. They're not going to escape the solution. Finally, let's do some questions that involve this principle. The practice prompt says solutions of equal molarity of ethanol, potassium iodide, and magnesium fluoride are compared. Which would have a lower vapor pressure and why? Now for these types of questions, what I'm going to say to you is key. You have to understand what happens to the colligative property when you add the solute. It's really easy to get crossed up. Wait a minute, does it lower or increase vapor pressure? Well, knowing what vapor pressure is key. Vapor pressure is the pressure exerted by a solvent on its surroundings. And if you add a solute, is less probability of those particles of the solvent escaping to the surroundings. So we can recall that vapor pressure is lowered by adding particles. Well, our three solutes we could have added are ethanol, potassium iodide, magnesium fluoride. From earlier discussion, we should know that ethanol, being a covalent compound, can contribute one particle to a solution. Potassium iodide is ionic with a 1-to-1 ratio of potassium to iodide ions, so there's two particles, and I'll draw that really quickly here. Potassium iodide is Ki, but since it's ionic, it breaks into potassium ions and iodide ions in water, so per formula unit you'll get two particles. Finally, magnesium fluoride is MgF2. Okay, magnesium is +2, fluoride is -1. So we would expect 3 particles per formula unit of magnesium fluoride. So the more particles, the lower vapor pressure goes. So for the first one, magnesium fluoride is our solution. Boy, this is difficult with a mouse. My pen ran out. I apologize. Which would have a higher boiling point. Keep in mind, what happens to boiling point when you add particles? It goes up. Boils at a higher temperature. More difficult to boil. Okay? Well, more particles means harder to boil, so ditto, magnesium fluoride is our solution. Finally, what happens to, which one would have a lower freezing point and why? A solution of magnesium fluoride would also have a lower freezing point. More particles lowers freezing point further. So none of these prompts led you in the opposite direction of where the trend for colligative properties goes. But what I expect of you is that you know what to expect of these 3 different properties when you add a solute. Okay, so it's important you know those things. That's the conclusion of video number 5. I hope it's been helpful to you. Please make sure you come to class with questions. There are a page full of questions on colligative properties, colloids, and suspensions in your practice packet. Make good use of it. We'll see you in class.